Section 7.2 is about some properties of exponential and logarithmic functions. And so recall that we learned in first semester how to take the derivative of an exponential and a logarithmic function with the natural base e. So if we take the derivative of e to the x, we get e to the x. Or if we take the derivative with respect to x of the natural log of x, we get 1 over x. However, those derivative properties are specific to an exponential or a log with the base of e. We can't just generalize those properties to other bases, such as base 2 or any base. So we're going to use logarithmic differentiation to prove the derivative rules for those two functions. We could always use logarithmic differentiation, but in the end, it will be easier if we just memorize these. So I know this is already worked out on the text on page 98, but I also know from my own experience, it can be tough to read along with the text and understand this example. So let's look at this example that will be general to any base a. So if we have the exponential function y equals base a to the power of x, a could be any base that is not 0 or 1, including e. So if we start off with y equals a to the x, again, we could use the process of logarithmic differentiation to be able to rewrite a to the x. So we would take the natural log of both sides. And I know this is already written out in our notes, but I'm going to write it out as well. So then, using the properties of logarithms, just like we did in section 7.1, we could rewrite natural log of a to the power of x as x times the natural log of a. So all of those steps so far are just algebra, we're just using properties of logarithms to rewrite an equation that was y equals a to the power of x. But now, if we enter in with our calculus step, we can take the derivative. So the derivative with respect to x is really what we're doing between these two lines. Oh, I'm going to just write a ddx right there. So we get 1 over y times y prime, because we took the derivative of y with respect to x. So that implicit differentiation is when we multiply by dy dx or y prime. And then on the right side, again, we're using the product rule. So the derivative of x, which is 1, times the natural log of a, plus the derivative of the natural log of a, which is 0 because a is a constant. So the natural log of a is also a constant, times our first function x. Now, we didn't really have to use the product rule right there. We could have just said that the derivative of this is the natural log of a, just like the derivative of 7x is 7, or the derivative of negative 3x is negative 3. The derivative of any constant times x is the constant, which is the natural log of a in this case. Regardless, we could rewrite this. I know there's not a rewrite step in the text, but 1 over y times y prime equals the natural log of a. And then lastly, we want to eliminate that 1 over y on the left. So we could do that by multiplying both sides of our equation by y. And we get y prime equals the natural log of a times y. Well, remember that y is a to the power of x. So we get the natural log of a times a to the power of x. And that's going to be our rule for taking the derivative of an exponential that's not, that doesn't have the natural base e. Now, we could always take the derivative of exponentials that way. So for example, if we fill that in with e, so if y equals e to the x, y prime would be the natural log of e times e to the x. Well, that's still true because the natural log of e is 1. So y prime is e to the x. So that's why our derivative rule for exponentials base e is really simple. But when there's another base, we have to multiply by the natural log of that base. And that just comes from the process of logarithmic differentiation. So that's our general rule for derivatives of exponential functions. Let's talk about derivative rules for log functions where we have a base other than e. So let's suppose we have y equals log base a of x. If you remember from Algebra 2, if our goal is to isolate x, we would do what's called, we would exponentiate both sides of that equation. So if I start out with y equals log base a of x, and I want to get x by itself, I know the inverse function to a logarithmic function is an exponential of the same base. So since this log has a base of a, we would exponentiate both sides of this equation with a base of a. And that means we basically turn the stuff on either side of the equal sign into the exponent. So that's how we go from line 1 to line 2 of this, I guess we could think of this as like a little proof. So a to the power of y equals a to the power of log base a of x. And just like in Algebra 2, log base a of x and the exponential function a, those are inverse functions. So they undo each other and we are left with just x on the right. So a to the power of y equals x. X is not an exponent, because the logarithm and the exponential function have reversed each other. They've undone each other. So x is just x. All right, from here, we have now really rewritten a to the y as an exponential function. So we could go back through that process of logarithmic differentiation, but we're really going to do what we did up here, except we got to be careful because this is not a to the x, it's a to the y down here. All right, so when we follow that derivative rule, we know that we're going to take the derivative on both sides with respect to x. I should put this in front, but I'm going to write it like this. This is like, don't write this on a test, but for our notes, I think that's fine. So we're going to take the derivative of both sides with respect to x. Well, let's actually do the easy side first. The derivative of x with respect to x is 1. You could think of that as dx dx, but it's just 1. The derivative on the left side, so the derivative of a to the y, we could use our rule up here and we would say, well, that's the natural log of a times a to the power of y. But because we're taking that derivative with respect to x, we've got to be careful because this is still implicit differentiation, meaning that when I hit that y, I've got to use the chain rule and multiply by dy dx. So we have using our rule up here, the natural log of a, I know I'm writing this in a different order than it is to the left, times a to the power of y, because it was y to start with, but times y prime. And again, that y prime comes from that implicit differentiation and the chain rule. We could just think of that as an application of the chain rule. So now if our goal is to isolate y prime, well, everything on the left-hand side of our equal sign, those are all factors, not terms. So we could just divide both sides by, I'm going to rewrite it this way, a to the y times the ln of a. All right, so when we do that, we now have y prime equals 1 over a to the y times the natural log of a. But our goal is to write y prime in terms of x. So instead of a to the y, if we go back up to the equation that we got when we exponentiated both sides, we got a to the y equals x. So we could substitute x for a to the y there. So we get y prime equals 1 over x times the natural log of a. And that is the general form for the derivative of any logarithmic function of any base, not just base e. But we could check that real fast with base e. So let's say that our original function is y equals the natural log of x. So that would be log base e of x. If we use this formula, so to speak, or if we use this derivative rule, that means y prime is going to be 1 over x times the natural log of the base, which was e. And just like before, the natural log of e is 1. So we end up with 1 over x. So that's why our derivative rules for the natural log and the exponential with the natural base are easier than when there's a different base. Now, you could figure that out with logarithmic differentiation every time, but instead, I think it would just be best to memorize everything in this box. So we already know some of this information. So for example, we already knew that when we take the derivative of e to the x, we just get e to the x. But more generally, we could think of when I take the derivative of any exponential, I get that exponential, so base a to the x, times the natural log of a. So this is the new, more general rule that we need to remember when the base is not e. We also know, way back from Unit 2, that the derivative of the natural log of x is 1 over x. But more generally, if we want a rule for any log of any base, then we need log base a of x. So that's going to be 1 over x times the natural log of whatever the base is. And then lastly, we have this antiderivative rule that when I take the antiderivative of e to the x, we get e to the x plus c. Well, we can also generalize that when we take the antiderivative of a to the x, we get a to the x divided by the natural log of a. To prove this last integration formula and why this general form works, it's hard to do the proof. Like, it's hard to prove that with inductive reasoning. So let's actually just look at this from the standpoint of taking the derivative. So if I have a to the x over the natural log of a, so if I look at what's in that box there, if I take the derivative of this, I could think of this as like 1 over ln of a, all that's just a number, times a to the x. So if we take the derivative of that, we know that 1 over the natural log of a is just coming along for the ride because that's a constant. So when we take the derivative, we get 1 over the natural log of a, and then the derivative of a to the x is a to the x times the natural log of a. So those two things undo each other, and we're left with a to the x. So if the derivative of this, like let's say this was y, if y prime of a to the x over the natural log of a, if the derivative of that is a to the x, then it stands to reason that when we integrate a to the x, the antiderivative is a to the x over the natural log of a. So to really work that forwards like a proof, like we did for the first two generalizations, I would honestly have to think about that a little more, but we can make that, or we can prove that to ourselves in a very informal way by taking the derivative of a to the power of x over the natural log of a and realizing that we get a to the x. So we could prove that integration rule that way. All right, so at the bottom of the page, each of these examples corresponds with one of those formulas that are in the box for our exponential or logarithmic functions. And we've just got to be really careful here that we're mindful of things like in the second example where we have 3 minus x. So we still have to think about the chain rule, and we could either do it the long way using logarithmic differentiation, Or we could try to apply these rules with things like the chain rule in mind. So I'm going to go for option 2 just because the process of logarithmic differentiation is so many steps. So in this first example, when we're taking the derivative of the exponential 3 to the x base 3, we could apply that very first rule. And we get 3 to the x times the natural log of 3. We have to be careful in the next example because we have 7 to the power of, I'm going to call it some junk. So 7 to the power of the junk. And anytime I catch myself saying the word junk, I know that means I'm probably going to need to use the chain rule. So if we use our exponential rule for when we have a base other than the natural base, we know that we're going to have 7 to the junk still. So we get 7 to the power of 3 minus x times the natural log of 7. So far, we're just following, again, this formula that's in the box. But because of the chain rule, because that's 7 to the power of 3 minus x and not just plain old 7 to the power of x, we still have to multiply by the derivative of 3 minus x, which is -1. So we might end up rewriting that as like a -1 times the natural log of 7 times 7 to the power of 3 minus x. And just a quick reminder, that would be the same as saying the natural log of 7 to the power of -1, which is 1/7, all of that times 7 to the power of 3 minus x. So those kind of go hand in hand. All right, this last example is really just an extension of any chain rule example. We didn't need this lesson. Sorry, that's my cat in the background meowing at me. We could have done this one back in Unit 2. So when we now have e to some junk, that's fine. We know that it's the derivative of e to the junk is e to the junk. But again, we have to use the chain rule since the junk is not just an x. So the derivative of e to any power, or I shouldn't say any power, but e to the x is going to be e to that same power. So x times sine of x. But then we must multiply by the derivative of x times the sine of x. So we got to be careful that we use the product rule here. Derivative of the first times the second is sine of x, plus derivative of the second times the first is x cosine of x. So that's what we get for that third derivative. So on page 99, I know we haven't gone over one of every type of these yet. I would love for you to pause the video and try these problems on page 99, and then I will work them out in the next video. And if you feel like you don't need to watch it, you can fast forward through to see how you did.